Good morning and welcome to Tech 240 for Wednesday, March 24th. In this class session, we're going to talk about single-phase AC motors, which are really important because they're so ubiquitous. You're probably surrounded by them right now. But before we get into that material, let's take a look at the schedule. So there's actually nothing due today on March 24th, but at the next class session, or the day of the next class session on March 29th, we have Lab 13 that is due by 11:55 p.m. on that day. And then we have Lab 14, that's going to be on transformers, which we're going to talk about in the next class session. That's going to be due on April 4th. And then if we look ahead about a week and a half, we have Exam 2 coming up in the not too distant future. So you have the vast majority of the material that's going to be on Exam 2 already, so you can start organizing your notes for Exam 2. We'll talk more about Exam 2 in the coming week or so, but I'll give you a little preface or preview of what it's going to be like. The intention for Exam 2 is for it not to be cumulative. You know, that being said, I can't get away from everything that we covered in the first third of the semester. You just can't really get away from Ohm's law and the power equation and some kind of basic electricity fundamentals. You can't really get away from that in a course that's about electricity and electric circuits and electric machines. So there will be some of that. I can't say it's not cumulative at all, but I can guarantee that there will be no KVL, there will be no KCL. You won't have to be using relays to design circuits and things like that. So the intention is for it to be just on the electric machines material that we have covered since the first exam. All right, so it's not intended to be cumulative. All right, so that's a little bit about Exam 2, but again, we'll talk more about that in the coming week or week and a half. That will be on April 5th. So make sure you mark your calendars and be ready for that by April 5th. All right, so that's enough for the schedule for right now. So we're going to start talking today about single-phase AC motors. Arguably, these might be the most important kind of motors, actually, because if you are wanting to use a motor in your household, well, first of all, you probably want to plug it into a wall, so it's going to be AC, because that's what we use on the electric grid. And if you're in your house or your apartment, it's going to be single-phase AC, because you don't have three-phase AC in your house unless you live in a factory or a warehouse somewhere. Probably you don't have three-phase AC in your house. Basically, nobody does. You'd have to do something pretty special to get three-phase AC in your house. So this presents a little bit of a problem for us because if you recall from a couple class sessions ago, we said that what's common about all AC motors is that they have a rotating magnetic field. The magnetic field itself actually rotates around the device, which is different than DC motors, right? That was different. The easiest way to get a rotating magnetic field is to use a multi-phase machine, which usually means a three-phase machine because that's by far the most common type of multi-phase machine. Three-phase machines are pretty common, but you can't use them in your house or your apartment or in any residential setting because you don't have three-phase AC. If you had three-phase AC, it's really easy to get a rotating magnetic field because you've got coils of wires around the stator, like one set of coils here, one set of coils here, one set of coils here, and you just hook up one set of coils to each phase. So first phase A is at a high positive voltage, so you get a magnetic field here, and then phase A goes back down to about 0 voltage, and phase B goes up to a higher voltage, so now you got a magnetic field in this orientation, and then that goes down, and then phase C ramps up to a higher voltage while phase B goes down. So now I've got a strong magnetic field in this orientation, and then it just repeats. It goes over and over as our phases A, B, and C do that kind of complex shape that I've drawn a couple of times where phase A goes up and then goes down, and meanwhile phase B has gone up and then it's going to start going down, and meanwhile phase C is going up and then it's going to start going down. So That's the easiest way to get a rotating magnetic field inside of an AC motor, but it's not always practical. You don't have, as I've said several times already, you don't have multi-phase AC in your house. So all we have is single-phase AC in our house, and that's a problem because if I just have these two coils right here, this one set of coils, and I apply single-phase AC to it, what's going to happen is that I'm going to get a oscillating magnetic field. When I have a positive voltage, it's going to be a strong magnetic field in this direction. And then when it flips and goes negative, then I'll have a strong magnetic field in this direction, right? Or the opposite of whatever I just said. So you get what I call a pulsating and oscillating or flipping magnetic field, where it's kind of going like this. But that is not rotating. That is not a rotating magnetic field. So if it's not rotating, it's not going to be able to exert any torque on a rotor that's inside there. It's not going to create any rotational torque that could get that rotor started. So that's a problem for us in our AC motors because that's what we want. We want to get our rotor started so that it's rotating around. And this pulsating and flipping magnetic field, it's kind of intuitive, right? Like this is not going to be able to cause rotation in the AC motor. So we have to be kind of clever, and we have to introduce a new concept in today's class. And I kind of like the way this class is organized because we just introduce something called capacitors today when we're talking about single-phase AC motors. But it's kind of convenient that we just introduce capacitors today. We don't really talk in detail about capacitors today, but it's kind of nice because we'll just kind of gradually introduce them. And then later on in the semester, in the last third of the semester, we'll talk about AC circuits, AC circuit analysis. And then we will have to get into a little bit more detail about capacitors and also inductors. But by that time, we will have already had an introduction to capacitors and inductors. So it's kind of easing you slowly into some of the components that are important for AC circuits like capacitors and inductors. It turns out the most common way to create a rotating magnetic field in a single-phase AC motor involves the use of capacitors. So capacitors are pretty important for our discussion of single-phase AC motors. I know that you probably don't know much about capacitors, if anything, and that's totally fine right now. That is the point of today. We'll talk about what capacitors are and how they operate, just a little bit about how they operate, because that's important for us to understand how we're going to create this rotating magnetic field when we only can supply the machine with one single phase of AC electricity. All right, so we're almost ready to start our discussion over on the document cam, but I'll tell you a quick story just to kind of motivate this. So the story is from about either 2 or 3 years ago. It's funny how time passes by so quickly, but 2 or 3 years ago in the fall, I know it was in the fall, it was in late fall, probably September, and it was one of those heat waves in September where it was probably 90-ish or 90, maybe 90 plus degrees Fahrenheit outside. So it was really hot, and what happened was our air conditioning in our house stopped working. So, you know, at least it wasn't July, I guess, but it was really uncomfortable because it was so hot outside, and you know, you get used to having air conditioning, and it's tough not to have air conditioning when it's so hot outside. So we did, you know, we messed around with the thermostat and tried inspecting different components of the HVAC, but I was teaching classes that semester, you know, like every semester, and so I didn't have a lot of time to mess around with it. And so after doing a little bit of inspection, I thought maybe it was something with the refrigerant in the system. But anyway, after a little while, either my wife or I, we called out an HVAC, heating, ventilation, air conditioning, HVAC technician, and he came out, and I wasn't there when he came out, but he poked around our system and did some tests and looked around, And what he found, the problem was this right here. This is actually a capacitor, and this is the capacitor that came out of the outside unit of my air conditioner system. So this is that, like, you know, the box that has the big fan in it that turns on and blows around. There's also a pump in there that's pumping the, actually a compressor, but basically a pump that basically pumps the refrigerant throughout the refrigeration system. So without this capacitor operating correctly in the system, it was a busted capacitor. Without this capacitor operating correctly, the motors would not run in the system. So if the motors aren't running in your HVAC system, it's not going to work, it turns out. So you're not going to get any cooling, and the air conditioning system is not going to run at all. So by the end of today, I think maybe you'll be able to understand why my air conditioning system a couple of years ago did not work with a busted capacitor. So that's maybe kind of an objective today. So we'll talk about capacitors and use that to understand how we can make single-phase AC motors run by creating a rotating magnetic field. All right, so I think that's enough motivating explanation. Let's go ahead and get into it. So I'm going to switch over to the document camera. Okay, first I just wanted to refresh your memory of the problem that we have with a single-phase AC motor. Here's a drawing of the stator of a single-phase AC motor, and this is a problem because I don't get rotation of the magnetic field inside here. I'm going to put a rotor inside here, whether it's a wound rotor or a squirrel cage induction rotor, doesn't really matter. But the rotor inside here is supposed to get dragged along for the ride with the rotating magnetic field, right? But the problem is if I have a single phase AC rotor, a single phase AC stator like this, then all I'm going to have is a magnetic field that expands as the applied voltage increases and then decreases and collapses as the AC voltage decreases, and then it flips when the AC voltage flips polarity, and then it goes more negative, and then it collapses again, and it just oscillates and pulsates like this. All right, so that's a problem because we don't get a rotating magnetic field around the stator, and if we don't get a rotating magnetic field, then it's not going to create any torque to rotate the rotor around the inside. All right, so that's the problem. In the case of a three-phase or multi-phase AC motor, we solve that by putting multiple phases. So I have a phase like this, but also have a phase over here and a phase over here, and we're going to fire or energize the coils of the three phases in succession, one after the other, to create a rotating magnetic field. All right, but we can't do that, not exactly like that, in a single phase AC motor because we don't have three phases available to us in our homes or apartments. So we have to do something kind of clever. All right, and what we're going to do is use a capacitor. And there's different ways we can use it, but first we need to think about what is a capacitor, what does it do? Basically, a capacitor is just two plates that are separated from each other by an insulating material. In this case, you can think of it just as air. That's fine, that'll work. Normally it's a paper or a ceramic material, something that's insulating. But for right now, you can just think about these two metal plates that are separated from each other by air is fine to think about for now. And think about what happens when I apply a DC voltage for now. All right, eventually we're going to apply an AC voltage, but just to get us thinking about it, think about a DC voltage. So I apply this DC voltage. What's going to happen? The current is going to go this way, right? So I have the current that is going to come from the positive side of the battery. It's going to come this way, and I've got charge flowing. That's what current is, right? Current is the flow of positive charge, right? We've said that before. Current is the flow of positive charge. So as it flows, we're going to get positive charge that builds up on this plate. All right, so I'm going to get positive charge that builds up on this plate right here. These are supposed to be all pluses. And then as I get positive charge, built up on this plate right here, it's going to repel the positive charges that were on this bottom plate down here. So I get the positive charges that are repelled from the top plate, they continue to flow down here, all right? At least for a very short time period, I get the positive charges leaving this plate and continuing to flow through the circuit, which leaves me with a negative charges on the bottom plate right here. All right, so I get positive charge that builds up on the top plate that repels the positive charge from the bottom plate, which leaves the negative charge on the bottom plate. And the positive charges continue to move in the circuit, and that is current flow. Now this happens for a very short time period until the capacitor reaches a full charge and it can no longer accept any more charge. And what is a full charge? Well, the capacitor is going to be fully charged when the voltage across the capacitor reaches the same voltage as the applied voltage. At that point, you won't get any more current to flow because look, this is acting kind of like a battery. It's got a positive side on the top, it's got a negative side on the bottom, so it's actually opposing the applied voltage right here. So when that happens, I get current to stop flowing. Current will not flow anymore. So what we can say is that capacitors pass DC current only until the capacitor is charged. What does that mean? It means when the voltage of the capacitor, I'm going to write that V sub C, that means voltage of the capacitor is equal to the voltage of, I'm going to say the battery here. So when these two voltages are equal, then they're opposing each other and no current is going to flow. After that, capacitors block DC current. All right, but think about what would happen if this was not a DC voltage source. What would happen if this was a AC voltage source? With an AC voltage source, I'm going to have the positive here and the negative here for a split second, and then it's going to flip. Then I'm going to have the positive down here and the negative up here. And it's going to flip every half cycle. So what's going to happen is the capacitor is going to be charged up in one direction for a split second. Then the applied voltage flips, and the current is going to go the opposite direction. So then the capacitor is going to discharge, and it's going to charge up in the opposite direction. And then the applied voltage is going to flip-flop again. I'm going to get current to flow in the original direction. So it's going to discharge the capacitor and then charge up the capacitor in the original direction again. So what happens with a capacitor in an AC voltage circuit is that the capacitor is repeatedly charged and discharged and then charged in the opposite direction and then discharged and then charged in the original direction and then discharged. And it repeats over and over and over and again, really, really fast. All right, so the voltage that builds up on the capacitor flip-flops with the applied voltage that you have right here, if it's an AC voltage. All right, so that's an important thing to know. The other thing that I really want you to pick up on here is that what happens first? Does the current flow onto the capacitor, or do I get a voltage on the capacitor? Well, the only way that I got a voltage to build up on the capacitor that's going to oppose the applied voltage is if current flows first, right? Current flows, and that puts a charge on the capacitor plates, and as a result of the charge on the plates, as a result of that, I get the voltage built up across the capacitor, right? So that's really important to know. This has an order to it. First, the current flows, and that builds up a voltage on the capacitor. So let's write that because that's important. In a capacitor, first, current flows onto the plates of the capacitor, which then builds up a voltage across the capacitor. All right, and there's a more succinct way of saying that first current flows and then we build up a voltage. What we say is that in a capacitor, current leads voltage. This is actually a really important concept. It's a really important concept for all AC circuits, and this is the first time we've talked about it. But this will be really important for the last third of the semester, to know that in an AC circuit, in a capacitor, current leads voltage. Actually, anytime you have a capacitor, current leads voltage. Doesn't even have to be in an AC circuit. Current always leads voltage in a capacitor. All right, and there's a mnemonic device to remember this, and the mnemonic that you need to remember is ICE. All right, the way this mnemonic works is that the C stands for the capacitor or capacitance, I stands for the current, and E stands for the voltage, like EMF, electromotive force. All right, and notice that in the word ICE, C's in the middle, and I comes before or leads E for the EMF, right? So if you remember this word, you can remember that I comes before E in a capacitor. So current leads voltage in a capacitor. So what we're going to do in an AC motor, a single phase AC motor, we're going to use this fact that current leads voltage, and thus current is out of phase with voltage. If you were to plot the AC waveforms, you'd plot the voltage and you would find that the current is not exactly in sync with the voltage. The two waveforms are actually shifted from each other. So what we can do, we can actually use that. Remember that it's current through a coil of wire that causes a magnetic field, right? It's the current that is causing the magnetic field. So what we can do is we can take this stator of an AC motor and we can have another coil like this. And what we're going to do with this coil is we are going to have a capacitor in series with this coil. So I may as well introduce the symbol for a capacitor. There's actually a couple different ways to draw a symbol for a capacitor, but I'm going to draw it like this. This is one of them, where you have a flat line and then a curved line. That's the symbol for a capacitor. So if I have that capacitor in series with this coil over here, which is actually connected to the same voltage source. This is the same voltage source coming out from the same points. I should maybe even draw them all connected to the same points, all right? To emphasize, it's the same voltage source. But what I'm going to have is one set of coils that is directly connected to the single phase AC voltage source. The other set of coils is going to be connected through a capacitor. And what that capacitor does, because of this, because current leads voltage and the current is out of phase with the voltage, they're not in sync. They're not the same waveform. And because of that, the magnetic field in this set of coils is going to be out of sync with the magnetic field in the main set of coils. And because of that, I'm actually going to get a rotation of the magnetic field. So that's actually the clever way that we can get rotation in a single phase AC motor. We use a capacitor. We use the fact that in a capacitor, the current through the capacitor leads the voltage that is applied to the capacitor or across the capacitor. And we recognize that it's the current through the coils that is causing the magnetic field. And if the current is out of sync with the voltage, then I'm going to have a magnetic field in the blue coils that is out of phase with the magnetic field from the brown coils. And because of that, I'm going to get a rotation of the magnetic field. I hope that starts to help you get an understanding of how we're going to create a rotating magnetic field in a single phase AC motor. But we're going to apply it in a couple of different ways with different kinds of AC motors. So I'm going to switch over to my presentation slides, and we'll talk about a couple of different kinds of single phase AC motors. All right, what we're going to talk about now are the most common kinds of AC single phase motors. These aren't the only kinds, there are other kinds, but these are the most common. So let's go ahead and talk about capacitor start single phase AC motors and permanent capacitor single phase AC motors. All right, so like we said, we have a problem with a single phase AC stator because we have no rotation. Remember, this is where we said we have the pulsating and flipping or oscillating magnetic field, but we don't have a rotating magnetic field. But what we can do is we can use the principles of a capacitor, and we know that the charge builds up on the capacitor because current is flowing onto the capacitor. And only because the current is flowing onto the plates of the capacitor do I get a voltage across the capacitor. So the current flows first, then we get a voltage. So we can say that current leads voltage in the capacitor, and the mnemonic device is ICE. In a capacitor, C, I, current, comes before E, voltage. So if you were to take an oscilloscope that plots the waveforms, what you'd see if you plotted the current through the capacitor and the voltage across the capacitor is something like this, where the red curve is the current and the blue curve is the voltage. So you can see that the current is leading or coming before the voltage. And remember, it's the current through a coil of wire that creates the magnetic field. So what we're going to do is we're going to have one set of coils on the single phase AC motor that is directly connected to the source, the single phase AC voltage source. We're going to have another set of windings on the single phase AC motor that is connected through a capacitor. And that capacitor, what it's doing, it's creating a phase shift for the current relative to the voltage. All right, so now I'm going to have current flowing through that second set of windings out of phase of the current flowing through the main set of windings. And if the currents are out of phase through the two sets of windings, then they're going to create a magnetic field that is not in phase. And so in fact, there will be a rotation of that magnetic field as first this set of windings creates a magnetic field, and then this phase creates a magnetic field, and then this phase creates a magnetic field, and then it keeps rotating around and around the stator of the AC motor. Okay, the rotor that's inside there, haven't said anything about that yet, but usually it's going to be an induction rotor. So it could be a squirrel cage, like we talked about last time, or it could just be a wound rotor, where you just got a whole bunch of wires that are each offset in angle from each other. Either way, both of them are induction rotors, and there's no connection to the outside, to the stationary side. So there's no connection, no electrical connection to the rotor, which is really nice and convenient. The first kind that we're going to talk about is the capacitor start single phase AC motor. And let me preface this by saying that you might remember me saying a previous time that if we have just a pulsating and oscillating magnetic field, that's actually enough to keep the rotor continuing to rotate. It's just not enough to get it to start to rotate. So what the capacitor start single phase AC motor is going to do, it's going to have that second set of windings with a capacitor in it, and it's going to use that along with the main windings to get the motor started. But then once it starts rotating, and once it's up to speed, it's actually going to disconnect the set of windings that have the capacitor connected to them. All right, so here's a couple pictures of it. We've got a capacitor in series with the auxiliary windings, or the start windings, sometimes called start windings. And the start windings here are shown in the black wire, and the main windings here are shown by the white wire. So the white wire is always connected. We always have coils for the main winding that are always producing this pulsating and oscillating magnetic field like this in the picture. But the capacitor is connected to the start windings. And the important thing about those start windings is that they are connected to a centrifugal switch. A centrifugal switch is something that disconnects, via centrifugal force. It's the force that feels like it's pushing outward as something is rotating around. It feels like you're being pushed outward. Well, you can make switches that disconnect once something is rotating around due to that force that's pushing the switch out. That's something called a centrifugal switch, and they're fairly common. And you can connect the start windings to that centrifugal switch so that once the rotor is up to speed, it actually activates that centrifugal switch and disconnects the start windings. All right, so the start windings are connected initially to provide a rotating magnetic field, but then once the rotor comes up to speed, you disconnect the start windings and you're only using these main windings shown here in the white wire right here. And that's enough. It actually continues to operate just with that pulsating and flipping magnetic field. Here's a schematic of a capacitor start single phase AC motor. Here's our main winding that's always connected to our AC input voltage. But then we have this start winding that is connected via a centrifugal switch and a capacitor. So this switch is closed when the rotor is below a certain speed, and then when it speeds up above a certain speed, this centrifugal switch opens so that you're no longer energizing the start windings. All right, and inside here, the way it's drawn is a squirrel cage induction rotor, but like I said, it could be a wound rotor also with coils of wire at different angles. All right, the pros and cons of a capacitor start single phase AC motor. Obviously, a big advantage is that it runs on single phase AC, which you have available almost everywhere, unless you're out in the wilderness somewhere. And this one actually gives better starting torque than the permanent capacitor that we're going to talk about next. We'll talk about the permanent capacitor single phase AC motor next. But this one, the capacitor start single phase AC motor, gives you better starting torque because those start windings are designed with low resistance, and they're designed for a large amount of current to flow through them, which thus gives you a strong magnetic field, which thus gives you a strong starting torque of the motor. So with this design, you have a stronger magnetic field, and thus you have better starting torque to get that motor rotating. The disadvantages, this is true of all AC motors. You can only adjust the speed by adjusting the AC input frequency. The power capacity and the torque are not as good as the three-phase machine. And these don't really come in large sizes. In fact, it says 10 horsepower, but really most of them are a lot smaller than that. And you might even recall way back at the start of the semester, you calculated how much power you can actually get out of a standard wall outlet that has a 15 amp circuit breaker, 120 volts, 15 amps. If you remember what that was, here, let me do that calculation because I don't remember what it was. 15 amps times 120 volts is 1800 watts divided by 768 watts per horsepower is 2.35 horsepower. So 2.35 around that horsepower is the most you can get out of a wall outlet anyway with a standard 15 amp circuit breaker. Some have 20 amp circuit breakers, but it's not going to make a huge difference. So it doesn't even really make sense to make AC single phase motors much bigger than that anyway, because you can't use that. The most power you can get out of a typical single phase wall outlet is only about, less than 2.5 horsepower. So typically the power output of these motors is really limited to a couple of horsepower. Clearly, if the capacitor fails or if the centrifugal switch fails, it's not going to work well. If the capacitor fails, then the motor's not going to start because you're not going to get a rotating magnetic field. If the centrifugal switch fails, then it's either going to run poorly with a lot of vibration because it's not designed to run at full speed with the start windings in the circuit. So it's not going to run well, or you could actually damage the start windings because, like I said, those start windings are designed to allow a large current through them, which creates a large magnetic field, which creates a large starting torque, but it also creates heat as you get a lot of current to flow through those start windings. So those start windings are really only designed to operate for a short period of time to get that motor started. And they do their job well. Normally, when they work, they do their job well by creating a large rotating magnetic field, creating a large starting torque, but they're not designed to operate for a long period of time, and they can overheat if they do. So you could damage the start windings if the centrifugal switch fails, which would leave the start windings in the circuit for longer than they're supposed to be. The next one gets rid of the centrifugal switch, and we call this a permanent capacitor, single-phase AC motor, because in this case, this second set of windings, which we call the auxiliary windings, not start windings anymore, because they're not just used for starting the single-phase AC motor. What we've got here is that the auxiliary windings are permanently energized in the circuit through a capacitor. So there's going to be a set of main windings, and there's going to be a second set of windings called the auxiliary windings, and they're going to have a phase difference. There's going to be a phase difference for the current going through the main windings compared to the current going through the auxiliary windings. And because there's a phase difference in the current, there's going to be a difference in the magnetic field. The magnetic field is going to be out of phase, which creates a rotating magnetic field, which creates a torque and causes the rotor to rotate inside the motor. All right, we now call this sometimes a permanent capacitor or sometimes a run capacitor. Pros and cons of the permanent capacitor design are that, again, it runs on widely available single-phase AC, so that's a good thing. It also does away with the centrifugal switch, so you don't have to worry about that centrifugal switch failing, which makes this design a little bit more reliable than the capacitor start single-phase AC motor. The disadvantages here, once again, you can only adjust the speed if you adjust the input of the AC frequency. And the starting torque is not as good because those auxiliary windings are designed to have current going through them all the time when the motor is running. So they're not designed to allow a burst of high current through them like the start windings were from the last design. So because of that, you have a smaller or weaker magnetic field, and therefore you have less starting torque than the capacitor start design. Once again, if the capacitor fails, then your motor's not going to work. Kind of like my air conditioning unit that I mentioned a little bit ago, because you don't have a rotating magnetic field, so you're not going to have anything to create a torque to get your motor started. The last motor design I want to talk about today is called the universal motor. It's pretty interesting because it can run on either AC or DC. So to start talking about this, think about the series DC motor. It looked like this. And remember when we talked about how to reverse the rotation direction of a DC motor, we said that you have to flip the polarity of the current going through the armature relative to the field, right? So you got to flip one or the other, but not both. Because if you flip the polarity of the current going through both, then you can test this by by using the left-hand rule for motors. You can try this out, and you'll see that if you flip the polarity of both, you will not change the direction of the Lorentz force, which is going to cause the motion. All right, so what you have to do to reverse the rotation direction is flip both, but not one, but not both. All right, so if we thought about the series DC motor, we talked about this before a few class periods ago. We said that if you flipped the polarity of the applied DC voltage, you will not change the rotation direction of a series DC motor, because you would be causing current to flow backwards through both of these. All right, so you could actually have whatever applied voltage you want here. It could be positive or negative, or it could oscillate between positive and negative, and you'd still get rotation of this motor in the same direction, right? So if I can say that I can apply a positive or a negative voltage to it, and it's still going to rotate in the same direction, I can apply an AC voltage to it where it flip-flops back and forth, and it's still going to rotate in the same direction. It's going to continuously rotate in the same direction. It's not going to stop and reverse direction when the applied voltage changes and goes negative. It's going to continue rotating in the same direction, even as my applied voltage goes positive and negative and positive and negative, like it does in an AC voltage. All right. So basically, a universal motor is very similar in construction to a series DC motor, but there are a few things that we changed to make it operate a little bit better than it would if you just applied AC to a series DC motor that was designed as a series DC motor. So if something is designed as a universal motor, there are a few changes, minor changes in construction to make it operate better on AC. The first change that you make is that the core material of the field winding, all right, so that means the piece of metal that you wrap the wire around to make this electromagnet right here. So usually you use a piece of steel, a piece of metal, usually steel, and you use that for a core, like a cylinder, while you wrap the wire around to make this field. All right, so what's going to happen is if you just have a big chunk of metal, a big solid chunk of metal that you wrap the windings around, and you apply an AC voltage to that winding, what's going to happen? Well, that core is a conductor, and you're getting a magnetic field created by the wire wrapped around it. Not only that, but you're getting a changing magnetic field, which makes for the motion. It's a relative motion between the magnetic field and the conductor, because the AC voltage is constantly changing that magnetic field. So that gives you motion, actually. It's a relative motion between the magnetic field that's changing and the conductor. So what do you get? You get generator effect in the core of that winding. And you don't want that, because when you get a generator effect in the core of that winding, you get current that's just flowing in loops. It's just flowing around inside the core of that winding. If you get current to flow inside there, you get heat, because you have resistance inside there. So you're heating it up, and that is energy loss. So you don't want that, because you're going to lose efficiency of the motor. So what you do, you don't use one big solid chunk of metal that you wrap the windings around. What you do is you make the core out of a bunch of narrow slices, like really thin slices of sheet metal, that you laminate together, and you glue them together. And now you're still going to get get some induced voltage in there, but the current has a harder time flowing inside there, because it can't pass easily between those different layers, those laminations of the core material. So if the current can't pass as easily through them, you're not going to get as much current to flow through the core of this winding right here. And if you don't get as much current to flow, then you're not going to get as much heat created, and you're not going to have as much losses. energy losses. So this is all about improving the efficiency of the machine by minimizing something called eddy currents. Eddy currents are the name that we give to those currents that would exist and be created and be flowing inside the core of that field winding. And they're bad. We don't want them to exist. So we minimize them by using a laminated construction. Laminated means a bunch of thin sheets stacked together instead of one big hunk of material. All right, so that's how we make the core of the field winding. And the other thing that we do is for that winding, we haven't talked about inductors yet, but inductors really are just a coil of wire. Any coil of wire is an inductor. And we're going to talk more about inductors in the last third of the class, so I don't expect you to know very much about this right now. But what an inductor does, what a coil of wire, which is an inductor, what it does is it offers a resistance to a change in current flow. So you've got current flowing through this coil of wire, and it doesn't want to stop in reverse direction. It's almost like the current has momentum. That's not really what it is, but it almost acts like the current flowing through this long coil of wire has momentum, and it doesn't want to stop flowing in that coil of wire and reverse direction. It doesn't want to do that. All right? That's the way it behaves. All right, so that creates a problem for an AC motor because we need to be able to reverse the direction of current flow. That's what an AC motor does, is it applies an AC voltage in one direction and then flips it, and then it takes it back to the positive half cycle and then the negative half cycle. So we're continuously changing the voltage, which is going to continuously change the current in this field winding. So we want to reduce the inductance. Don't worry, we haven't talked about that unit yet, but we will. We'll talk about inductance later on in the semester. But I need to introduce it right now because this is a big deal for a universal motor. We want to reduce the inductance of the field winding in this motor to make it more efficient. So what we do is we make our field winding have a few fewer turns. It doesn't have quite as many loops of wire in this field winding right here. That's done to minimize the inductance of this field winding, which minimizes the resistance to the change in current flowing through that electromagnet. Okay, universal motors are really common in small appliances like food processors and blenders and coffee grinders. All of those have typically universal motors. And they have some big advantages. Obviously, they run on AC or DC, which is a big advantage in and of itself, although we don't always utilize that, but it is an advantage. This one is definitely a big advantage. It can rotate faster than the synchronous speed because there's nothing that's limiting it to the synchronous speed. In this design, it's like a series DC motor. So in this design, it's not like the rotor is getting dragged along with the synchronous speed, with the rotating magnetic field on the stator. It doesn't work like that. It works more like a DC motor where you create a Lorentz force because of the current carrying conductor in the magnetic field. All right, so there's nothing limiting it to the synchronous speed here in this case. So it can actually rotate faster than that. It can rotate a lot faster than that, which makes them good for, like I said, blenders and coffee grinders and food processors, things like that. It works a lot like the DC series motor, and it has really good torque, just like the DC series motor. The disadvantages, as you can see, it has brushes. This right here and this right there represent brushes. So you got all the issues with brushes. They're kind of loud and they have a shorter lifespan. Normally in a small kitchen appliance, you're not going to replace the brushes. You're just going to throw it out and get a new one. So, you know, it's not ideal, but that's what people normally do. So it's going to have a lower lifespan than it would if it was, say, an induction machine, an induction motor. And like a DC series motor, it's difficult to regulate the speed, to control it to an exact, precise speed, because it's basically a DC series motor, and there's a complicated interaction between the magnetic field here and the armature. And when you change one, you change the other. If you change the counter EMF, because there is counter EMF in here, because it's operating like a DC series motor. So when you have counter EMF, that's going to reduce the amount of current that goes through the armature, but it's also going to affect the amount of current going through the field winding. So because of that feedback, it's going to be difficult to control the speed precisely, just like in a DC series motor. That's going to wrap up today's presentation on single-phase AC motors. So hopefully at this point you have a little bit of an understanding about capacitors and how capacitors work, and how we can use capacitors to create a magnetic field that is rotating around the stator in a single-phase AC motor. So it's important to remember that current leads voltage in a capacitor. Remember ICE, that's your mnemonic device. Remember how we can create the rotating magnetic field by using two sets of coils. One's going to be the main winding, usually called the main winding, and the other one would be either your auxiliary or your start windings, depending on what type of motor you're talking about. And those are going to be connected in series to a capacitor. All right. In full disclosure, we don't have time to talk about every single different type of single-phase AC motors, and there are different kinds of single-phase AC motors, but the vast majority of them do employ a capacitor. They do use a capacitor to create that rotating magnetic field. All right, so let me know if you have any questions about any of the concepts that we covered today. This is going to wrap up our discussion in the class of motors, of all kinds of motors. We spent, I think, about 3 class sessions talking about DC motors, and this is, I think, the 3rd class session we've spent talking about AC motors. And the next topic that we'll talk about in the next class session is transformers. Transformers, by comparison, are really simple compared to different kinds of motors that we've been talking about. If you understand the principles of motors and generators, then transformers are going to be really straightforward and easy to understand. So that'll be actually a pretty simple class, actually, when we talk about transformers. And then in the class session after that, we'll do some review. And the class session after that would be the 2nd exam. So that's coming up. Okay, well, that's about it for today. So like always, let me know if you have any questions, and I'll see you next time.